Hello, everyone, and thank you for joining us for today's e-showcase, AquaPrime Advanced Primary Treatment for Additional Capacity, Construction, and Energy Savings. I want to take a moment to thank our sponsor today. Thank you so much to Aqua Aerobic Systems, a Metawater company. I also have the pleasure of introducing our presenter today, John Dyson. John Dyson holds a BS degree in chemistry from Longwood College. He has experience working with many treatment technologies in all parts of water and wastewater facilities. With over 30 years experience, John has worked on many projects varying in size up to 600 MGD. John's experience with a variety of technologies gives him a unique ability to evaluate and determine the best solutions for clients. In addition, he has been involved in the introduction of several new technologies throughout his career, including clarification processes, membranes, filtration technologies, and absorption process. And without further ado, John.
Thank you very much for allowing us to present today on the Pile Cloth Media Technology. I'm going to share my screen now. It should be good. All right, and I'd like to thank everyone for joining us today, and hopefully you find this very helpful and informative. At the end, there'll be the ability to ask questions, and I'll try to answer all your questions that you may have. For today's webinar presentation, we're going to basically go through a few things when we talk about the use of Pile Cloth Media Filtration technology. We're going to put a definition to what primary treatment is. What's the difference when you use Pile Cloth Media Filtration to create what's now considered in our industry advanced primary treatment? The actual operation, how are we doing this with Pile Cloth Media Filtration in an application such as advanced primary influent? How you could possibly locate it within the treatment facility, and I know we're talking about primary treatment, but there are some dual capabilities and benefits due to the high quality effluent that's produced here. Go into some projects. Everybody wants to know about specific projects and operating facilities. I have one frequently asked question that a lot of people ask throughout, so I go into that also, and then have some conclusions at the end, and then we'll finish with questions. So advanced primary treatment, I always like to start off with the idea that, we have to compare it to what the industry standards are there. We have conventional treatment, which is classically basically horizontal or circular primary clarifiers. And what we expect from those is typically 40 to 60% TSS removal and 25 to 40% BOD removal, and the other parameters there. If we want to create an enhanced primary treatment effluent, one way you could do it with existing technologies like clarification is to add coagulants there to achieve maybe 60 to 85% removal, as you will see that you can achieve with Pile Cloth Media Filtration. But that comes with more solids to handle within your facility, also the operating costs associated with it. All right, so what are you achieving with advanced primary treatment and the use of a Pile Cloth Media technology like the AquaPrime technology? So what you achieve here is without chemical addition, we have found we can easily remove 80% of the solids and generally achieve greater than 50% BOD removal, and respectively same about for COD also. What does that mean to a treatment facility? Well, what it means is if you're trying to just do this with an existing facility with no capacity increase, you could save on your energy costs, which we know aeration is the largest energy cost within a wastewater facility. So that could be a 20 to 30% energy savings. So that's very dramatic because of the reduced BOD and increased BOD removal provided by the technology. What we really see in a lot of cases is really more increased capacity. People are looking at the technology due to its small footprint to be able to add capacity in facilities. A lot of our facilities that have become landlocked, and so we need to every bit of land available to maybe expand the biological capacity at the same time. The other thing that's a change is just like with the energy savings in the aeration system, now you're taking more primary sludge out. And if we just compare a conventional primary system to the AquaPrime technology, Pile Cloth Media, we're changing that 40% ratio of primary sludge to waste activated to a 60-40. That gives you more digestible material to utilize in anaerobic digestion, and that can give you 30 to 40% more biogas, all that can be beneficially used within your treatment facility. So what are the big changes that we made? The idea and technology of cloth media filtration has been around for a very long time, but to apply it in a primary application, as we're talking about today, we had to deal with the different water characteristics from a tertiary now to primary influent. Well, we have floatables in the water that need to be removed. So basically, we had to make modifications to the system so it was capable of handling that. A core of the work is still done by the cloth media, and the cloth media is a unique thing, and the ability to be able to clean in such a difficult application of raw primary influent coming in there. And we also did changes to the settled solids in the system. In primary applications, we have settled solids that are readily settable. I always like to use the analogy that in a primary clarifier, particularly if you think about a horizontal, we make them deeper at the front end where the hot solids are coming in initially, because a lot of those settle out very rapidly in that location, the first 10 to 20%. And what we're actually achieving with the AquaPrime technology is the ability to basically do 3 methods of solids removal. So it's unique in its aspect versus any other technology there. So how does the system work? So basically you have influent flow coming into the system. If you have multiple units, you use the influent weir to split the flows. All right, because it's an outside-in filtration process, floatables rise to the surface, settleables can settle between the discs. Other solids will be collected on the surface, and you filter the water. So we're utilizing all those 3 means for solids removal. But as solids build up on the cloth, you're creating head loss, and the water level will rise in the filter. As the water level rises, it reaches its backwash initiation point. And now we start to rotate the center tube and disc segments at this time. And basically what you're looking at is the backwashing that's occurring. We have these backwash shoes on either side of the system. And as we're filtering the water, we're pulling it back at a really, really high backwash rate to efficiently clean off the solids that are on there and basically continue. So the filter's in service all the time, even during backwash. This is just showing an 8-disc system where we wash 2 discs at a time. So one after the other. If we had a 24-disc system, we wash 8, 8, and 8. As I mentioned earlier, those settleable solids that have settled down between the segments and the walls settle into hoppers now that have a steep slope on them. That steep slope allows some concentrating to occur, gives room for storage of that for periodic extraction. Generally, that's every 8 to 10 backwashes that's occurring, and you suck those solids out. You basically just want to prevent a blanket of sludge from forming in the system. Those floatables have a natural tendency to be pushed to the effluent end of the tank because influent in on the right hand, coming on the right hand side, pushes and creates a flow in that direction. We just do a hydraulic removal by opening the valve on the submerged trough. So that's the basic operation. It continues to operate automatically like this. So it's very effective, very simple in terms of operation. So what does it look like in concrete? Well, this is a larger unit than that package unit that you were looking at. You would have a common influent channel for multiple units, your influent weirs, the center tube. This has their megadisc size disc in there with 24 of them. Then you have a pump and valve gallery. In that pump and valve gallery, of course, you have your valves for backwashing and settled solids removal. We have a dedicated backwash pump and we have a dedicated solids waste pump. So you can ensure that you can backwash when you need to, all along with removing solids as necessary, because we know we have varying conditions in the primary application. We have a scum trough that's attached at the effluent end to collect scum and those floatables, fats, oils, and greases, effluent weir, and effluent channel. I like to always show this kind of section view from influent into effluent in because you can better see the scum trough in the background there, the draft mechanism that rotates the whole center tube assembly with the disc segments. You can see the end of the center tube there, but then you can also see these hoppers. And due to the configuration of these basins, and just to give you a kind of a scale here, those hoppers are approximately 1 meter deep, so a little bit, about 3.3 feet deep. And so we're actually settling solids and having some concentrating occurring within the process. And of course, your pump and valve gallery. So where could you apply the technology within a treatment plant? So if this is a conventional treatment plant with existing primary treatment, one place you could apply the technology is after primary clarification. And polish off, say, pushing the flows through your primary clarifier. This would further clarify that water, reduce those solids to the secondary process. More classically, what people are thinking about is actually replacing the existing primaries with AquaPrime because of the small footprint to allow for more building of biological basins, those type of things. But another benefit is because you produce such a high quality, that high 80 plus percent removal of TSS, the water quality is of such nature, particularly during wet weather events, that generally the effluent during those events is going to be at levels of probably less than 30 milligrams per liter, which then could allow it work in a dual function to do your advanced primary treatment along with peak wet weather flow management, allowing you to not have to oversize the biological system there during these peak flows. Other applications would be when you think about not every plant has primaries. There are many technologies out there like the Aqua SBR technology, those things. If you apply the AquaPrime technology in advance of a process like an SBR, oxidation ditch, etc., one of the benefits that you're getting here is you're going from no solids removal to a dramatic reduction in that. And what we found, and I'll have a case study later on that showed that we could dramatically increase the capacity of those existing SBRs. And the same principle of wet weather management occurs. We're also seeing interest in applying the technology because of the nominal size removal, the 5 micron size removal of our cloth for this primary application. It becomes an excellent barrier in front of MBR technologies that are there too, because it removes all the hairs and only very small, very colloidal particles actually pass through the cloth. So how did we get started on this? We have a great relationship with the Four Rivers Sanitation Authority, where we do our R&D work. We have an R&D system building on this wastewater plant, plus other demo equipment built on this facility. And they've followed our research for a long time and at this facility. But we took one of our initial pilots that we constructed, and we actually ran it in comparison to their plant, just to get a comparison of what we would expect out there. And initially, before we had decided the cloth that we've developed specifically for primary applications, was we tried a nominal 10 micron cloth and a nominal 5 micron cloth that we have here. And we tested these to determine how they would perform. And our initial research showed that, of course, so we got good removals with the 10 micron shown in blue, but we got even better removals with the 5 micron cloth. And then we saw respectively the same thing with BOD. We decided to design the cloth for the primary application specifically around the 5 micron because we were seeing that we had the ability to do advanced primary treatment along with the wet weather treatment, producing a very high quality effluent, so that dual purpose. So we selected that. That's there. But one of the things I think is that's so unique about the technology is its ability to handle a range of solids but produce a consistent effluent. And the reason I think that is important is clarifier performance that we usually generally deal with is good when the flows are low, but as flows go up, you get carryover to occur. Your removal percentages can drop pretty significantly. As you can see here, we were testing different flow rate conditions, different influence were coming in, and you can see a very consistent effluent with that nominal 5 micron um, cloth media. So when you actually look at BOD removal, you can actually also see here that there's a very consistent number. Now there is more variations here, and that's usually due to the soluble fraction varying day to day in any wastewater influent conditions that are there. So a lot of times people ask, how does your system perform? And as I said, we've done a lot of R&D work, and we did a test with their AquaPrime technology called Pile Cloth Media Filtration with the SBR following behind. And you can see our removals from the raw influent through the AquaPrime and the effluent of the SBR. So, very good performance in terms of TSS and COD. Here we in operating, you see some of the level of phosphorus removal that was occurring. Most of that was occurring through the biological process of the SBR. But you can also see here that with those high performance in terms of TSS and BOD or COD removal, you see here in terms of total nitrogen, and in this case, we're able to achieve total nitrogens on average less than 5 milligrams per liter, with the light influent coming into the SBR. So, people always kind of ask the questions, when you have low levels of carbon because you're doing such a high removal efficiency, can you still nitrify, denitrify? Yes, you can. So actually moving on, as I mentioned earlier, the district has followed their research and testing for years, and then they decided as a need to upgrade, do some upgrades in their facility. They have endeavored on the construction of a 30 MGD AquaPrime as part of the plant. So their plant has is designed for an average flow of 40 MGD, max of 80 through the whole biological train. You can see the influent conditions here. Why were they doing this? Some of the primary basins, they have 10 horizontal rectangular shaped primary clarifiers was aging. Some of them dated back, I believe, almost to the mid 1930s. So they were, pretty old. So we're going to need in major rehab. The ability to have that increased removal because they also do cogen at this facility. So they were interested in removing even more carbon that was there. So this is the existing facility where what was the initial facility before the project started here. They are in the process of the exciting news, literally starting up the system as we speak. They're wet testing this week. Hopefully we'll have that goes well and speedy, and we'll actually start raw primary in next week. But it's good. They're going to go from their 10 units to 8 units because we built 2 AquaPrime units for a capacity of 30 MGD and within the footprint of one of their combinations of 2 primary basins. Eventually, in the second phase of the project and work going on at Four Rivers, they're adding 10 MGD of Aqua Narita, which is aerobic granular sludge process that's there. So it's really exciting time, a lot of construction going on. So, but related to the advanced primary treatment aspect, as I mentioned, that we're in the phase one, where we are, was constructed the two filters, low lift, and a gravity thickener for backwash handling. They have the aqua Narita phase. It's under construction now. It's probably a year and a half to 2 years out for completion. After that, the plan is to endeavor on another 30 mgd of advanced primary treatment in the next set of two basins, and still have the remaining 6 newer basins available to handle really wet weather flow conditions once they have both phases of advanced primary treatment completed. So a lot of people ask, what do you do with your backwash water and the settled solids? Well, in this case, the facility already uses thickeners to take their primary waste, thicken it up before they send it to their gravity belt thickeners. So that was ultimately the plan here. This was the design conditions that we utilized for the design of the thickener. This is the artist rendering, what the facility is going to look like. It's going to be a very beautiful facility. You can see the low lift on the right-hand side. In the center portion between the center two covers is where the gallery area is. Those pipes, valves, and backwash pumps. The filters are actually under the silver color covers here. At the other end is your thickener sludge pumps, and of course the thickener. And this is all constructed within the footprint of 2 of the existing primary basins. So in that same footprint, we added more capacity and a lot of auxiliary equipment that's there. This is a view from one side. This picture was actually taken on March 30th. So a lot of work has been done as of today. So a lot of change. This is the other side, changing very rapidly, but we're literally at the point of putting water into this. So we're really excited about that, and there'll be a lot more information and data to be presented in the future. I'm going to talk about one of the older projects that we have. Is Oak Hill facility. It's called the Minden Road facility. That's there. In this facility, basically, it was an existing SBR facility. Had an average day flow of about 0.5, 0.6 mgd. They needed to expand the capacity, increase their average day flow because they were bringing in additional flows from a neighboring town. So they had to take their old SBR system from 1.6 up to as high as they could get it. In this case, we determined that was about 2.65 mgd. The way to do that without adding any more SBRs, because the site was very constrained, we were able to introduce the AquaPrime technology, and that is removing, 80+% of the solids generally from the system in advance. So it allowed us to increase the capacity within the SBRs. So what's at the facility? You have screening and grit removal. They added the AquaPrime along with mechanical thickening to the system. They kept their 2 existing SBRs at the facility. We did pilot test as we were introducing the technology. These were the results. This is what we use for determining the capacity of the SBR technology and how much capacity we could get out. And I'll go into how we achieve more capacity. So footprint-wise, the original Aqua SBRs took up a footprint of almost 12,000 square feet, including the digester and contactor. So if we to get to the capacities, we would need at least 2 more SBRs for the increased capacity. They were able to put in really a storm basin. They don't use it as an EQ basin. They keep it very low. Very little wastewater in it until about the time of rain. That was built there. It's about 7,500 square feet. But because of the small footprint of the AquaPrime technology, we're able to put that facility on top of that storage basin, and that include the AquaPrime units, 2 duty, 1 standby, along with the thickening equipment. So able to achieve it in a much smaller footprint. This is what it looks like inside. The 3 units here. You can see the backwash pumps. The buffer tank is where the backwash and settled solids waste go. That is then transferred to the mechanical thickener where the solids are thickened up. How did we achieve the increased capacity? So no clarification, no primary treatment in advance. With an SBR, we generally, in this case, due to the requirements, we were able to do 5 cycles per day per SBR. By reducing the loads greatly, that allows us to shorten the mix fill, react fill, and react stages dramatically. Of course, we did some upgrades to the SBRs and DO control, but this allowed us to go from 5 cycles per day to 8 cycles per day on the SBRs. By reducing this time, we also reduce energy usage in the SBRs and while we increase the capacity. In the first year of operation, we of course monitored the results of the whole plant. You see influent conditions, you see effluent conditions coming from in green from the AquaPrime unit, and then the effluent from the SBR. So plant was easily meeting its permit limits and having excellent performance. So a lot of people, kind of want to know what it looks like when it's operating. So here's a video. It's done some time lapsing on it, but basically influent flow comes in, spills over that weir. We're time lapsing, so between the backwash periods, the water level will slowly rise. Okay, here as the flow comes in, you can see on the right-hand side is where the scum trough. This becomes submerged, unsubmerged between those backwashes that occur. But what you will see here is as the water level gets up here, it'll fill that scum trough. As it continues on up, just about equal to the weir height there, will initiate the backwash will be initiated. Then we'll see the chain start to move here right now, and you start to see the water basically start to drop, and basically we're backwashing the system. You see it drops pretty quickly. So the process continues to do this, and time after time from an operation. If it was scum removal, and I like to show this, is it's coming up like for a normal backwash, and this is scum removal is generally done every 8 to 12 hours on a system. So basically, as it's coming up, again, the trough will become submerged here, but after it's submerged, the level comes up, and we open the valve on this trough, and because of that influent flow coming over, the flow over the weir, we're able to clearly remove the scum that's there. Another question a lot of people ask is the sludge, and what do you do with it? In the case here, they do mechanical thickening, so they take the 2 waste flows, add polymer, and you can see going onto the system, it's very efficiently dewatering out. You can see this is the other side after it's just come around, and it's getting really thick. So they get about 10 to 15% concentration very easily, and they mix that with their waste activated, aerobically digested, and that gets fed directly to their final dewatering at their facility. Done a lot of testing at facilities, and one of the other places is in California. It's been part of the California Energy Commission project that is still ongoing in multiple phases. In one of the early phases of testing, we installed a full-scale unit, and it's still located in Linda, California. Plus, we ran pilots, and when you have a new technology, people want to know how pilots compare, how to full scale, how long things will last. So testing was done at 3 different locations utilizing 2 pilots and the full-scale unit. And you can see TSS, COD, BOD, TKN removals, very similar from installation to installation. So you can see here that we're building this experience that we know consistently that you're going to achieve that 80 and 50% removal efficiencies. So what does it mean? The data was taken from the phase 2 testing. You can see here that by reducing those loads, looking at each individual facility, you could anywhere from 25 to 35% reduction in aeration requirements would be there. So major energy savings. Other savings that could be associated with the technology, if you're building new biological basins, you can make them smaller, which means you need less mixing energy. And again, you can have more biogas production. Um, as I mentioned earlier, when something is new, uh, is you want to people want to have confidence that the technology is representative. So we actually took that full scale unit at Linda, put a pilot unit, had them match up so they had identical flows coming in at any given time. And we did a study in comparison. So you see influent conditions, you see filter effluent for the full scale filter, the pilot, the averages. So you can say to me, it's well within the errors of measurement, 85, 89 between the two systems in terms of TSS removal. In terms of BOD removal, very similar type of results. Again, we're achieving there. In terms of COD removal, very similar results also. So we feel real confident that anytime we do a pilot test at a customer's request, that our pilot results really match up with full scale. Uh, Also, they do mechanical thickening with that full scale system. So we're feeding generally about 0.2 to 0.3% to the thickener. They try to operate the system 2 to 5, but they can easily get 8 to 10 with this volute style thickening that's there. The one thing that we did find difference, and we kind of knew this in advance, was that there would be a difference because pilots needed to be shippable without much field installation, those type of things. We actually knew that we didn't have as much hopper room. So, but you can see here whether it's the pilot or the actual full scale filter, the TSS in the backwash was the same in the for COD and roughly for BOD. Uh, in terms of the actual solids removed from the settle, the blow that have settled the blowdown, now because the pilot has a much shorter hopper, used in the example in that full 24 disc I mentioned earlier, that hopper is about a meter deep, so you have some storage capacity. In the pilot, we only have about 18 inches, so that's there, so we can't store as much and get as much concentrating impact there. But we knew that kind of from a design standpoint. So in that case, the pilot is conservative in its nature. And this is, this raw data, that was used to come up with those settle solids conditions. So some other projects, and there's always interesting projects. Hamilton County is a project that we pilot tested not too long ago, and plant's under construction, but it was average day flow is about 0.3 mgd. They have a biological capacity about 0.5, and they're looking to expand that, but they also have big wet weather flow conditions, 5 to 7 mgd at times. And so at this facility, they have an existing contact stabilization process that's there. You have the prime units, the mechanical thickening with the system. You have your influent wet weather flow. So here we're doing advanced primary treatment along with wet weather treatment to achieve the numbers. So it's also when you do pilots, you see different things within the facility. You can see the influent conditions during the primary, it was pretty dilute. It was kind of a wet period. But we also did see when we did wet weather, call it actual wet weather events, that we had a very big first flush. And you can see 500 TSS, and we had about 30 TSS. We averaged overall probably in the neighborhood on this study about 15 coming out over the whole wet weather event. So you can see how the technology can be used for that advanced primary and wet weather. So we've done a lot of studies now. These are just the primary and or the primary slash wet weather studies. We've done a lot more actual wet weather studies too, but they're not here. But we've built a lot of confidence through these studies and the plants that we have started up and under construction there. But what we found is this is all the places that we pilot tested. You can see the average removal in brown for TSS. You can see the BOD, COD removals, more variations, of course, that we would expect that due to soluble fractions. But as a general rule, that number really works out good. If I look at the data and I keep this running total, that we basically are averaging 83% in terms of TSS, 56 in BOD, from all the studies, 51 for COD, and about 15% TKN. So, very confident in there in terms of those numbers when I say that 80-50 rule. What I think is more interesting, we've tested a extremely wide range of conditions from very low influence to very high influence conditions. I'm just talking more about TSS, but we see it for all the different parameters. But you see, these are the that upper range. We had a study that averaged 400 milligrams per liter coming in. That meant we had days that were 500, 600, 700 coming into the system if we were just averaging 400 for the study. But you can see because of that physical barrier, very small band here in terms of effluent TSS, and of course with each of the other parameters, very similar in terms of results. So other parameters people asked, how much fog are we removing? We here, based on the data, it's not, I wouldn't say the perfect test, but we definitely see about 40 to 50% fog removal through the process. In terms of phosphorus removal, this is just particulate, so no chemical being added. So we're just taking it, removing phosphorus as that. And we actually see, fractional soluble amounts of BOD. I really think this is colloidal materials that we actually remove through the filtration process that when you filter a raw sample for soluble BOD, you do still have some colloidals that do pass through. And have the data, for the range of information and how they may vary there too. So one of the most frequent asked questions that people asked is about the carbon management with BNR processes. And with the 80-50 rule that I would say there, everyone is asking, what's the impact of the low carbon on the process? So there are possible, several different possible solutions that if you're concerned about that you can do. And we'll go through about 3 solutions here. One solution is you really technically don't have to actually treat all the flow. If you want to have a desired influent condition for your secondary process, you could actually treat a portion of the flow through the AquaPrime unit. They'll let a portion go around. So, and then send that flow to your secondary process. So you get a much smaller primary treatment system there, but you get your ideal condition that you have. That's an option. So, how does that work mathematically? Say you have 250 influent, we're getting that BOD down to 125. You wanted it about 175. You would just, look at that ratio to create that optimal influent condition. Another option is kind of, what you saw with the Four Rivers installation. You can treat that flow, the filter backwash, settle solids waste, send that to the gravity thickener as we're planning there, allow that to thicken. We found in some testing that we've done in terms of settling characteristics, etc., we'd expect about an 80% removal, maybe a little bit higher, of the solids that are in the supernate coming off of that. You could actually, knowing that that's the case, you could, and this is a small 10% waste stream, return that to the secondary process as supplemental carbon. So that it's a 90-10 ratio. So in that case, if you say 250, the effluent from the AquaPrime, the Supernate, it could be anywhere from 300 to say 450 in the worst case, and you would get your ideal concentration, say 160, 170. That's there. Another option, which is people are all starting to think about because everyone's looking to do more BioP within their different processes, is you could do the advanced primary treatment and actually take and do primary fermentation, take that, create your BFAs that are there. So an example would be, 50, say you got 50 parts of BFAs, you take a portion of those out when you remove those solids in the process, but then you add those back in utilizing the side stream fermenter. You're going to be able to feed that, increase your uh, available BFAs for BioP. So to the end here, just want to kind of finish up with a few comments. Hopefully you've seen that the AquaPrime and Pile Cloth Media Filtration can give you a small footprint, a very high quality effluent, the potential to increase secondary capacity of the existing basins in the facility, energy savings in your facility or biogas production. It's simple to operate. It's well proven. The ability to maybe gain dual treatment aspects with wet weather treatment. And ultimately, I like to always say, when you're looking at different technologies, what's the right solution for my facility? It's really looking at a full 20, 30-year evaluation. And one of the things I think you will find is when you can reduce energy, when you can reduce footprint and construction costs associated with footprint, as we all know, concrete is very expensive today, that you will find that when you utilize a technology like the AquaPrime for advanced primary treatment, you can save a lot on construction cost along with other operating costs, making it very efficient overall. So I'd like to thank everyone for joining us today and open it up for questions.
Yes, absolutely. Please don't forget, just select the everyone option in your chat option and go ahead and submit those questions. We actually have one that's coming in. Are you using chemical in the PW Tech mechanical thickener on backwash and sludge?
Yes, in terms of the volute thickener in the PW, they're using polymer. They generally dose about 3 pounds per ton of sludge, so pretty typical usage in terms of what you would use in that type of technology.
And how does the PCMF perform with high effluent grease?
Okay, that's a very good question. We get this many times. Uh, One of the key things is we want to keep the cloth submerged. So the system's designed so the cloth will be submerged. So fats, oils, and greases that come into a system, uh, naturally will want to rise if it can. There will always be some stuck to other solids within the system. But in terms of that, we've had customers that have been concerned about it. One specifically took a 5-gallon bucket of Crisco that they heated up and dumped it in the system, and they found that most of that came to the surface and had no negative impact. They also came up because they were so concerned about this. We fed for 3 days 200 parts of vegetable oil to the system, and of course a lot of that went to the surface, and we still saw no negative impacts. I've been in this business a long time, so I, I never say never. So when I joined Aqua and was to introduce this product, intentionally, fouled the cloth. And one of the things that we found is Dawn detergent, the industrial version that you use for your home dishes, works really good to clean any oil and grease off if it was to occur there. But we feel like having the float removal and the design of the submergence protects the filter pretty well in terms of fog removal.
All right, perfect. We have time for maybe one more question. We are already at the end of our presentation, but I'm going to go ahead and do this one last one. All those that were not responded to, we will pass your questions on to our sponsor and have them respond to you via email. The last question is, what is the specific energy consumption in terms of kilowatt per hour per M3 wastewater filtered?
That's a difficult question because usually we do the analysis on a year basis and don't convert it down to that. Um, it really depends on the size of the system. There is some savings, so I'd have to maybe look that up and maybe can answer that via email to you.
And I am actually going to post John's contact information right there in the chat if you want to grab that real quick, just in case you have some specific questions that you want to reach out to him about. You can do that. And we are going to go ahead and conclude today's presentation. We certainly appreciate John coming out and presenting, and we definitely will thank our sponsor as well. This actually concludes today's e-showcase. Thank you all for attending. The recording will be available at webfiresguide.wef.org. We will send all registrants an email tomorrow with this link. Please visit our event calendar to sign up for a future webcast. Thank you, John. We really appreciate it.
Thanks everyone for joining, and I'd like to thank Beth for hosting this today.